Oh, um, I gave this talk a little while back at a conference, and I just decided I might as well record it and stick it on YouTube as well. So this is what this video is. Um, the title of this talk was 10 Practical ML Use Cases in Observability. So it's kind of like just 10 recipes of ways to use ML in observability. There's, I think, still a lot of low hanging fruit in observability when it comes to machine learning and actually using ML within observability tools. And that's what this talk is just trying to show, like 10 practical things that are not that hard to implement and actually probably, some are already, some are typical and some I haven't seen yet so far, which is strange. And so that's what this talk is. So I will just kind of run through these use cases. Um, the title of the talk was 10 practical ML use cases in observability. So I jazzed it up for the conference a little bit. So we leaned into I kind of thought it was looking like a bit of a listicle. So I leaned into the whole listicle idea here, where so we've jazzed it up for the conference, where it was, you won't believe these 10 amazing AI use cases in observability. So we're not doing ML here, we're doing AI now, apparently. Um, so there's a couple of things to bear in mind at the start. These are like, some of these are hot takes, some of them are themes that will be present in a couple of the different use cases. So first hot take number one is that observability lags when it comes to ML adoption. So if you think of lots of different industries like banking, insurance, marketing, online content recommendation systems, all these other industries, they use ML to the core of what they do. It is the product basically in a lot of cases. And when it comes to observability, we haven't got that far yet for some reason. It's there's We still have basically, the way I think of it is, we have all this fancy plumbing that's kind of moving all this data around from different systems and putting it in different storage locations, and we have agents and we have, you know all these different protocols, but none of them really kind of actually take a moment and actually try and process the data or actually use any ML to glean more insights from the data. It's still a bit like, old school. We put it all in one place and maybe then you can do stuff with it. So there's a lot of kind of places where I think ML could be another useful tool, and it should be just another useful tool. It should be boring. It shouldn't be sexy. It should just be, yeah, like, use ML for that, no problem. Um, and that's the second. That kind of leads me to my second hot take, which is ML as UX. So we're still, a lot of observability is still basically, at the end of the day, you're looking at a screen of dashboards, and it's like, now what? You're just looking at dashboards and trying to figure out. It's up to you now to figure out what to do next, and that's a bit savage. It's kind of old school, and there's a lot of ways where we can use ML as the UX. So instead of just some human deciding which charts are on the screen, which dashboards are on the screen, that's useful because there's a lot of expertise and domain expertise typically built into that by the time you're looking at that screen. But there's also another way, which we can use ML to surface things that might be of interest, ML to find useful patterns. So that's where this other kind of theme of ML as UX comes in, and I might try and point it out as I go. Um, our third hot take is that, like, the ML stuff is kind of relatively easy here. So it's the design that's hard, and this leads into a little bit the picture on the right hand side there. This is the famous Google black box picture where they have a paper and they talked about all the systems it takes to get an ML system into production, all the moving parts, all the components, and you can see that actually the ML part itself is just this little small box in the middle. And that's typically what you want, especially when you're starting. You want to use as simple an ML model, a simple an ML platform, a simple an ML algorithm as you can get away with, and then build out from there. So, and the time back to hot point number one is that in observability we have a lot of this stuff already built. So we have a lot of these data pipelines, we have a lot of these low latency systems for getting metrics, logs, traces into the right places, and making it all indexable and searchable, and all this fancy plumbing, which is what I kind of think of it as. We actually have a lot of this hard work is done, so it's really just the ML part that I feel is a little bit behind still. Um, and so that's where, actually designing these systems and how they all make together, how they all come together and how you get useful products out of them. That's the hard part, and that's where I think the last one there is, like, data products are still cool. We seem to have stopped talking about data products a little bit, but that's all this is. It's just data products, and ML is just another way to build data products. Um, and then these last few are, like, not that controversial. Obviously, I'm not saying we have self-driving observability yet. We don't. Anyone that says that and they have automated root cause terms like this, we're not allowed to use, and they're banned. So we don't have self-driving observability, and anyone that tells you that is basically trying to probably sell you snake oil. But that's not to say that we can't use ML in useful, applications where it's just another tool in your toolbox that you can use. And so that's where we still have like human in the loop. Obviously, we're not saying, for instance, if the ML thinks something is anomalous, that doesn't mean it's anomalous. It just means the ML thinks it's anomalous. It's still then onto the human to decide, yeah, it might be anomalous, but I don't care about it, because that's where the handoff is. And a lot of the stuff I'm going to talk about here, it doesn't just apply to metrics. It is mostly metrics because that's what I've been mostly working on, but it can also apply to logs, traces, and any types of observability related data, really. So the first use case here is probably the one where a lot of people start. Like it's the most well developed of all these use cases, I'd imagine, in observability. And this is just a question of, is my data strange or is it normal in some way? And this is basically the anomaly detection use case. So we're trying to say like, okay, and each of these questions is kind of, each use case is like a question and then a formulation with a recipe. And what you just kind of call out a few of the things you need to think about if you're implementing or building one of these systems is, what do you mean by normal? What do you mean by strange? And, what actually defines if something is anomalous or not. So this is the anomaly detection use case, and the inputs here typically are your metrics. The outputs are some sort of anomaly score. It can be a score or it can be like a 1 or 0 to say something's anomalous or not. And how you do it there is basically, there's 3 main kind of options. There's like rules. You can have hard-coded rules, business heuristics. You can have stats, which is more kind of like z-scores, median absolute deviation, things like that. And then you can have ML, where you actually just build some sort of machine learning model to basically either measure, you can there's 2 ways to do the ML. One is to do, and that gets into point number 1, which is forecasting versus unsupervised. So one typical way people use ML here is they try and build a model to predict the expected value of the metric, and that basically turns it into like a forecasting problem. So you're forecasting the next metric, and then once you actually realize the actual value, you now have an expected versus actual, and the difference between those two becomes some sort of input into your measure of an anomaly score. That's what typically people do by default, but the problem there is forecasting is quite hard for time series metrics. So there's another approach which uses an unsupervised approach, which is like a measure of surprise. So this is where you actually you have the data, you look at the data and you say, how strange is this data? Like, does this data look surprising, basically? And this is kind of like an easier problem to solve, because it's easier to spot strange data than it is to solve an actual accurate forecast model. So I'm a bit more of a fan of starting with unsupervised here, but both, it depends on the constraints you have in your system. Both make sense. And then a couple of questions that you need to ask here is like, where does the data live? Do you have all your data in one place in the cloud? Is your data all distributed? At the edge, is it on agents? So where your data live design matters, and it actually has implications for how you might design such a system. Where does your training live? So where do you actually do your training? Can you do it off in batch mode in some in the cloud somewhere where you have a little bit more leeway, or do you have to do it somewhere where you have other constraints in terms of overheads on the system and things like that? And the same question applies for inference. That because you could do training in one place and inference in a different place. This also matters here as well. Like, do you need to do inference and scoring live in real time? And there's a main, each of these questions, kind of the answer basically sometimes comes down to a trade-off between like the compute versus the latency. So if you have the best of both worlds, where you have you don't have to be so latent, and you can do all this stuff in the cloud, you can do the inference and the training in the cloud, then you have the best of both worlds, where you can kind of it's up to you to manage your own compute and latency, as opposed to if you need to do this in like an online fashion every second or every couple of seconds, then it's a little bit more different, and that might also have an impact in terms of how you implement things. Some of this stuff we've actually built at NetData. So there's a NetData Anomaly Advisor is actually, you can go and play with that. The link there has there's a demo room that shows how it all works. And then we have a blog, and we have a Python notebook that goes into detail, and we have a YouTube video that goes in detail exactly how our system works under the hood. And so yeah, that's anomaly detection. The last thing here is there's a couple like this. Anomaly detections are not just spikes. There's different types of anomalies. So that's what some of these charts are showing here, which is typically people might think of these kind of spikes or drops, but actually there can be lots of different types of anomalies. They can be drifts. They can be steps. They can be kind of context specific, where maybe the absence of a spike is the anomaly. So there's kind of a whole taxonomy of different anomaly types that some of them are on the screen here basically. Um, the next one is like a subset of anomaly detection. So this is basically, you're now looking at your dashboard. You have all these charts. What do I look at next? And typically the first thing you look at as a human is what has changed recently. So maybe you're looking at these dashboards for a reason. You're looking at the screen for a reason. Typically the first thing you're going to look for if you scroll through or as you're scanning things is really you're kind of just squinting and you're looking to see what's changed sometimes, unless you have a real clear idea of what you're looking for. If you don't know exactly what you're looking for, you're kind of just looking to see what's changed. And so actually picking out whether a time series has changed suddenly is like a really easy problem for ML, and this is not a problem. This is a simple little application of change detection basically. And so what we're looking for here is like typical change point detection. And so if a change may not be an anomaly, it can be a subset. So basically, maybe your time series does change. So a change could be normal. A sudden step change can be normal. But if you have a window of time you're looking at, then a change might still be interesting. So this is like short-term change detection, where you want to know what changed recently, suddenly, because maybe that's where I might continue my journey looking at what I'm trying to explore here. And so here we're looking at a similar sort of setup where the inputs are the metrics, and the outputs is basically an index of change points. So this is for each timestamp, a 1 or a 0, to say was this part of a change or not basically. And the two approaches here is again stats and ML. So this one's a little bit hard to do with rules. You could come up with some heuristics, but really at that point you'd be as well to just use some sort of stats, a statistical model. So basically, one example here is you can go a long way if you use things like median absolute deviation. Are pretty good at like capturing when a line changes suddenly. And likewise, there's a KS2 sample test, which is like a statistical approach where you're comparing distributions now over time to see if they're the same or if they're not the same basically. And if they're not the same, that's usually a sign of a change. And actually, that's the KS2 sample test is what we use in the net data metric correlations basically, where it's you highlight a time window, and within this window it's going to look at all metrics and compare the distribution for each metric from the highlighted window with the before the window, and basically just do that statistical test to see has there been any, like which of the metrics have changed in a statistically most significant way basically. And a couple of like things to think about, design considerations here is, do you need to do this in a streaming online manner, or can you do it in a batch mode? So what I say here is like if you have a highlighted window of interest, then you're almost in a batch setting where you have all the data you need. Whereas if you're in a streaming approach where you just need to do it in real time and streaming and then flag these metrics as they come in, that's a little bit slightly different. And that's where probably you would need to use something like median absolute deviation or something a little bit more fancy. And then as of course as well, there's always compute overhead here. That factors in, but if you do this in a streaming way, you can kind of do it where the compute overhead, you're never really, it's not like you're ever really continually crunching, thousands and thousands of data points. If ideally you're only looking at like the recent history, because what we're most interested here is like recent sudden short-term changes. So that kind of puts a little bit of an upper limit on the compute overhead in terms of how much data you're ever crunching. So number 3 here, this is one where I think this is like a good example of ML as the UX basically. So, and this is something that I haven't seen done before, but I think is obvious when you think about it. So this is like which alerts are the most important. So everybody has alert fatigue in observability, and it's a constant problem. And obviously you can tackle this by tuning your alerts and maintaining your alerts, like special alerts, basically special snowflakes. But another approach is to just accept that there's always going to be alerts and there's always going to be lots of alerts. So one approach here is to actually turn it into a ranking problem. So, and the inputs here are you have some alert, and the output is basically a score, or what's the probability of this alert soliciting a click from whoever it is I'm sending to. And so this is like a binary classification problem. And so if you think about this, it's actually, if you squint at this a little bit, it's not that far off from a marketing click-through prediction, basically. So each alert, if you think of each alert as basically an ad, um, now we're in the marketing land where we have, every ad gets a CTR score, and that's what determines, what you end up seeing as you Google something. Those ads, they're all come through CTR models and stuff like that. So there's no real reason why we couldn't use the same approach for alert ranking. Um, and that's all this is here, which is we're basically trying to, for every alert, as we produce each alert, we need to come up with a reasonable score, to be able to rank the alerts into alerts that people probably aren't going to care about because they don't tend to click on them. And at the top end, we have alerts that people probably maybe on average more than average do care about because we see that they solicit a reaction. And this is a nice one. This is actually a nice example where we can get fancy with an LLM here as well. So um, this is something we've been building recently where we actually are using just the alert text itself. So we have a template in say an email that gives you the alert, and that template itself with some of the values filled in literally becomes the story of the alert, and it's that story or paragraph that you feed into the language model along with the label of did somebody click this alert, yes or no, basically. And now you're into a binary classification framework, and this is where you can actually use your language model to do all the hard work for you. So you don't have to do all this kind of pre-processing and feature engineering where you do counts of the alerts in the last 15 minutes and ratios and all this typical stuff that you would do in a traditional ML sense. And now, because we have large language models, you can actually just let the language model do that inside the model. So as long as you give it the text, the templated text, it can actually it can do the feature, it can do the featureization inside the model. That's the beauty of neural nets, basically. And so the example here is this is on real data. So we basically we take you take 50% of alerts that had a click and 50% of alerts that didn't have a click, and that becomes your training data. And if we do this, this is something that we've actually done, and we're trying to get finished, basically. If you do that and train that model, you can come up with something that looks like a chart that looks like this now on the right hand side. And this is where we say, okay, of all the alerts that we produce, each of them now has a score, and that score is the probability that that alert will get a click. Now it's not the true probability, it's like a balanced probability because we've done this 50-50 balance here. So basically, if you get a score of like 50%, that means that this alert is as likely as any other alert on average, according to the model, to get a click. And but then it's like things that have a low score are much less likely, and things that have a high score are much more likely. So this is some real data here where you can see, okay, well, if we take those scores and take all of the alerts from yesterday, say, and we just rank them into their deciles, so the top 10%, all the way down to the bottom 10%, take those deciles, and then you look within each decile, what is the actual click rate, basically. And once you see the actual click rate, you can now get like you can see what your uplift is, basically. So that's what this chart is trying to show here, is that actually alerts that are in the top 10% are actually 76 times more likely to click than those in the bottom 10%, which is insane. Like if you had a marketing uplift, if this was a marketing campaign and you told your CMO, yeah, like I've got a 76% uplift in the top decile, that's gold dust. That's exactly what you want. And so there's no reason why we couldn't do similar approaches in observability where we can do a pretty good job. Instead of just kind of getting these alerts into your Slack, into your PagerDuty as quick as possible, we can kind of make a bit of a statement as to, okay, well, this alert has a score that's an 80% score, this one's a 10% score, and then give you the tools to actually see if you believe, if how often you agree, and if you want to prioritize or route those alerts accordingly. There's basically put more context onto each alert as opposed to just the template. We now have a bit more context where we've learned that from all of the alerts and from everybody, we've learned kind of which alerts are more likely than others to solicit a response from a user. Which is not to say that they are more important. It just means it is what it is. And this is the trick with how you frame these ML thing. It's gonna say it's more interesting in some sense to use it, but it's not to say that it's actually you could still have every now and then you might still have an alert that has a low value but actually is critical for you. So this is the tricky bit about how you come up with how you turn these into products for users. That's a hard part here. But I still think that's there's still a lot of use here that we could do in terms of alert ranking. Um, and if you go a step beyond this, then you could have this alert ranking and you could have the feedback as well to see, okay, how well does the alert rank actually line up with what people actually do when they see those alert ranks. And now you're almost getting into reinforcement from human feedback type systems, and then you could go really far. So this is an example. There's a whole lot that I think could be done with alert ranking. I think it's a bit sort of strange to me that we just produce these alerts and we don't actually try and put any more kind of enriched context onto the alerts, really, beyond just tags and labels and manual stuff. So here's an example actually basically of what I mean. So the input here would be the text below the dashed line. So this is the template where we're saying, like, literally name is systemd failed state. So this is the name of the alert. The status was from clear to warning. There's one systemd service is in a failed state, and it's an error classification. There's also 5 other warnings, and there's one other critical at the moment. So the model basically reads this text and basically gives you this score to say, wow, this is like an 84%. The probability of click here is 84% according to the model, which is much, much higher than average. So this is something that the model thinks is like really salient or impactful, versus something over here where we see MySQL slow queries. There's 25 slow queries went from a clear to warning. There's not much else on the system here. So the model says, like, people tend, like, from what I've learned as the model, people tend to not necessarily click on these compared to other stuff, basically. So that's why the 6% here. And you can see that in the reality now, neither of these was clicked. And this is the trick about alerts. The true CTRs are always very, very low. What you really need to do is get this rank to say, well, is the rank useful on average? But for each individual alert, it's hard to know. It's not like just because the model gave this an 80% score, it doesn't mean that 80% of the things in here are going to be clicked. It just means that it's a much higher than average. It's like a kind of an odds ratio type thing, which is a little bit tricky. But this is where I think you can package this up into more easy to understand. I think traffic light systems or different categories for users on the front end. Ideally, it'd be best to just give people this score and say, like, explain it to them that a score of 50% it's about as likely as an average. A score of 80% is a lot more than average. A score of less than 10% is a lot less than average, and then let the user make the decision as the human in the loop, basically. The next one is number 4. This is what different patterns exist in my data. So I like this one actually. This is one that I like for ML as UX that I was talking about earlier. So what we have here is you think of our dashboard, say, and we've got all these charts and all these time series on our dashboard, and one way to think of that is it's really just a big matrix of data, and within that matrix of data there's all these different wiggles and patterns that some line up together, and this is like perfect for a clustering and similarity use case, where we can actually just show you which different types of patterns exist within all these metrics and group them together into different clusters of the same type of shape, basically. And so there's 2 ways to do this. So the one way is the inputs here are, again, your metrics, and then the output is for each metric we're looking for just a cluster label per metric. So it's literally just an integer per metric to say this is in cluster 0, this is in cluster 2, this is in cluster 4, and then basically you order by the cluster label. And now it's really obvious here. Now you've got your kind of fingerprint of your system, so you've got all the different patterns going on here. And this is like the ML here is easy. We're literally just using k-means and some sensible heuristics. And so this is what I mean when I say like ML as UX. So this big, huge, crazy heat map on the side here is like an example of, I think, like 4,000 metrics on one system, and you can see that actually it groups into different clusters of behavior, basically. And so actually these are all the uptime metrics. They always kind of continually increase. You have things that are on off, like, so I think we've zoomed in here and we have an example where we've got like these metrics were not expressed and then they were expressed. We have a column of things that turned on at the same time here. We have some on off stuff here. These things all turned on at the very end. So if you quickly look at this, you can really easily see across your all of your metrics basically what different types of patterns exist, and then you can easily see which metrics are in each pattern. So this is like a one way to use ML as the UX, as opposed to, you'd never really get this if these were all just on charts and a big huge long dashboard and you scrolled and the order was kind of just some random order or some order that means some sort of structure based on semantics and things like that. It would be very hard to see that all these things are on at the same time until you have to kind of hold a couple of things in your head, scroll down, hold it in your head, and then you realize, oh, they're on at the same time, or so this is like a really easy way to do this, because the ML here is easy. The hard part is just the actual, how do you do this all on the front end. Another way as well is to do it based on the clusters themselves. So you can say, like, okay, instead of this heat map approach, you could look at it this way, where you see, like, here's the different shapes in your data, and you can then see each line that's a member of each of these clusters basically. And so I think this kind of scales pretty well as well, where you've got thousands of metrics. That's not a problem here. And the only trick is that you need to kind of normalize your metric first. So obviously all of these metrics are on different scales, they all represent different things, and so the trick here is to make these things all comparable. You have to normalize them first to put them on the same scale, and then that's why you can compare, something that might be, some of these might be like megabytes per second of traffic, and some might be CPU percentages. But when you actually put them on this normalized scale, where the max value is 100 and the minimum value is 0, you can now basically compare them all to do the clustering, because they're all on the same scale basically. So yeah, this is one I like. It's a good example for like ML as UX. And then a little bit leading on this is the fifth use case. I'll start going quicker. I'm going a bit slower than I thought it. This one is kind of like, you have a metric that you're interested in. So again, we're looking at some sort of dashboard. We're looking at a screen. There's some sort of time series. We're looking at that time series, and we're looking at the shape of this time series, and we're saying, what else is shaped like that? That's another one of these where, in our head, in our human brain, we're saying, okay, what changed? And then next we say, maybe, okay, what looks similar to that? Is there anything that looks similar to that? And again, this is like a really easy problem for ML. Metric similarity is like one of the easiest problems to solve basically. And there isn't even any models involved. It's not even that expensive if you're doing pairwise. If you can always do, if you don't do every combination of pairwise, then it's of similarity scores. It's not even that expensive, depending. So the use case here is, you have your metrics as an input. Your outputs now are a similarity score between. So you have your candidate metric A, and then you have your set of comparisons, which is a set of all the other comparisons, and you're doing a pairwise comparison of A versus each of the set of candidates basically. And then for each of those pairs, you're now looking for a similarity score. And the similarity score here can just be a distance measure basically. You can do fancy stuff, or you can just start simple with like a simple Euclidean distance or cosine similarity. And some sensible pre-processing basically, where you might sort of you might aggregate the time series so that you're not literally comparing second by second stuff. You might bucket the time series into different bins basically. And so this is an example here, a realistic example, where we're looking at, on the right hand side, we have like, an IO system IO in, and we see it goes up and down, and then there's this spike, and then so obviously the metric is 100% similar with itself basically, because it's just you're comparing the exact same thing with the exact same thing. And then when you scroll down, you start seeing like, okay, here's other metrics that are 99% similar, down as far as 90% similar, 80% similar. And here you can see, like in this case, okay, I know it was net data doing some disk reads and stuff like that. But you can really easily see now within the set of most similar metrics, maybe anything that's like 70% similar or more, is going to be things that also have that similar shape if you squint. And you can see here it's not quite as similar. You have to squint a little bit, and you can see these two spikes. You still have these two spikes, and so this is where we're trying to just say, what other stuff kind of has a similar sort of shape to this metric of interest basically. And this is just a metric similarity use case. So this is another one that's kind of easy because you're not really this can all be done on the fly. You can do all these comparisons once you have the data. You don't need to train any models or anything here. This is literally just this is just using a statistical measure. It's not even ML. Like cosine similarity is not even really ML. It's just a distance measure. Number 6. This is another one sort of alerts related. So what we're doing here is we're trying to basically see if we can predict an alert storm ahead of time. So we have all these alerts, and what we're interested in is, the real problem happens when we have lots of alerts at the same time. That's obviously a sign that there's something bad, something wrong has gone wrong on the system. And what we're trying to do here is we can take our inputs, which can be metrics, or it can be state transitions of alerts in the past, or anything else really. And what we're trying to do is we're trying to output a probability of n plus alerts in the next t minutes. So this is like a little bit weird sounding, but basically what we're trying to do is, and we can turn this into a classification model to say like, so is there, if we once we pick, what's this n plus, is it like 5 alerts, 5 or more alerts, and what's this t, is it 10 minutes? Then we're trying to actually just say, okay, what's the probability that it's going to be 5 or more alerts in the next 10 minutes? And now you're in a classification setup where you can say, you can now kind of go back over all your historic data and you can kind of generate these training data and these labels to say, okay, pick a random moment in time and then look forward and see if it happened and featureize what happened before. And there you have your kind of your observation. You can, and then you randomly can do this across, times when it did occur, times when it didn't occur. And so the problem now is we're trying to come up with this probability of an alarm storm, or whatever you call this, which is this measure across your system to say, once you have this model trained, what's the probability according to this model that there's going to be this alarm storm in the next 10 minutes basically. And the idea here is if you can do this right and you can actually make this work, you potentially can get yourself a bit more of an early warning. So once this probability score starts going beyond a certain threshold, then you can maybe have a little bit of a lead time before the alerts actually happen. And there's a trade-off here between like how willing are you to accept false positives versus false negatives, and there's a little bit of trade-off here. Is like if every time it goes past this threshold, even if 1 in 10 times it's actually valid and it did turn out to be an alert storm, maybe that's good enough for you. So that's where your tolerance for kind of how noisy or how useful these things will be is almost, again, it turns into like a UX problem. Like, how do you actually turn this into a product feature is the tricky bit. And so here, this is what we're trying to do is we're literally trying to give ourselves a bit more of a lead time, because trying to predict each individual alert is probably too hard, but trying to take a higher level view and predict something about the system itself based on the number of alerts, that's probably an easier problem 9 times out of 10. And obviously, if you can predict an alert with great accuracy, that's like the inverse of this whole problem. That's usually a sign that you've got a misconfigured alert, because if you can predict an alert ahead of time, it's 9 times out of 10 it's because it's a regular alert that happens every time and it's misconfigured. So that's like another use case here, which is the reverse of this, to find misconfigured alerts. But I haven't really gone into that, but it's just to worth pointing out. And so yeah, like here you have to know, like, okay, what's the window, what's the what number of alerts do you want? So there's a few parameters here where you can play around with and design. And then the question is like, what accuracy is good enough? So, if this, for me, I think like if this was to alert you and it was only actually correct 1 time out of 10, that would be still useful, like, because that 1 time it is important. It's so useful for your system. So this is where there's always these things that people try and think it has to be 90% accurate for it to be useful. The reality is it really depends on your use case, and there's a lot more nuance involved, and there's trade-offs and pros and cons here. And then it's not just about the ML accuracy, it's about, okay, well, how do you make this into a useful feature in your product where you can kind of de-risk some of that, so it's not the end of the world if 9 times out of 10 this is actually it's not sort of, it doesn't pan out that it gets an alert storm. Even if it's that 1 time out of 10 it is useful, and that's, I'm just using this as an example. Maybe you would really want 50-50, or you want better sort of precision. But these are called precision recall trade-offs in machine learning, and it's a common sort of thing, like, but it's almost like a design choice as well for what's your tolerance. Number 7 here is what are the drivers of this metric. So this is another one where we're looking at a dashboard, we're looking at some time series metrics, and we're trying to understand what's driving that metric. What is it that's driving that actual line I'm looking at here? And so there's a way to kind of tackle this, which is I'd say it's kind of clearest from the picture in the middle here, which is we're looking at this top line here, which is some metric, and what we're trying to look at here is we're trying to see how well can we predict this metric from some subset of other metrics, basically. And if we can do a good job, then, like, say we can predict this top line here, we can predict with a 80% accuracy based on these 10 other metrics. We've now got the drivers of this metric, basically. And like, sometimes it'll be obvious because there might be, you have to be careful because sometimes metrics can be very correlated with each other. So sometimes you need to maybe only use lagged values because it has to be based on data that's available at the time of the not available at the time of the metric. So you might need to use the lagged values of other metrics to predict this metric. This can depend on if you're looking for, like, typically what this is for like an explanatory use case where you're looking at a time series and you're trying to understand what's actually driving this metric, just pure explanatory mode, not for prediction or anything like that. It's just to understand the relationships between your data. So you can see here actually for this line we can see like this orange line is the most has the highest kind of feature score within this trained model. And you can kind of see it makes sense that when this guy goes up, the orange is very active, and you can see it, these particular two spikes here, the orange guy is driving it. Similar with the red guy. And then the idea here is, if I only had these 1, 2, 3, 4, 5 lines, can I build a decent enough model for this top line, basically, that's like explains enough of the variance in the top line? And if I can, then within these inputs, it's probably something that's a driver in some sense. Now, whether it's causal or whether it's more like a side effect, again, that's where the ML stops and the human in the loop kind of needs to come into things. So the inputs here are metrics. The outputs here is like an explanatory model of the metrics. And how we do this now is regression. So in this case, we're now in a regression setting where we're actually trying to just predict the raw value of the metric itself based on the lagged values of the other metrics, and see how good a job can we do, basically. And then the output here is like your summary, your one pager of, okay, here's the model, here's how good it is, and here's the metrics that explain it. And you could automate this to some extent, because if you just can't build a good enough model, then that's fair enough too. You're not able. But if you can, then you might be able to learn something from this and present this to a user to say, like, these are the drivers of this metric, basically. So it's a little bit similar to forecasting, but we're doing it sort of after the fact because we want to understand what's going on. So we have all of our data here, and we're now trying to understand what's the relationships within the data across metrics, basically. And yeah, so it's interpretability is what we're interested here, basically. The next one is so this is like one of the holy grails, I think, which is a recommendation engine. So that's why this probably has the least information here. So this is basically, what should I look at next? So we're in our dashboard. We've looked at one or two things. We've clicked on one or two things. There should be a little box in the corner that says, like, here's what you should look at next, basically. Similar to typical use cases like recommendation algorithms on YouTube or Amazon. People who bought this also buy this. There's like a lot of different ways to formulate this problem, and so that's probably why I haven't really seen it done in observability yet. And here the inputs are clickstream data, alerts. Basically, the inputs can be anything, and the outputs are recommended next action is the most general way, and that next action could be like to view this other chart or view this other dashboard, or maybe it's even instead of go from a dashboard, it might take you to an alert, or take you to a trace, or take you to a log line, or so it can be across systems, basically. And this is where, like, okay, you have to do this with a recommendation engine, but it's probably the hardest thing to do because it's very open-ended in terms of different ways you can formulate this, and it's also then hard to implement as well, because there's lots of building these things in real time, and you're into like ML platforms and complex systems for featureization. So this is like one of the harder, scarier ones. But it could be something that now that this could also be somewhere where like language models can help as well. If you can kind of package up the relevant little pieces of information and context into a way that a language model could understand these and kind of make sense of it all, then there is possible ways where you could use language models and things like that for recommendation. But I haven't seen it done yet, and it's a big kind of scary problem. But that's not to say it shouldn't be tackled. And the next number 9 now is typical one about can you predict the future? This is one that people always seem to ask for, even though it's probably not the most useful a lot of the time for observability. It's useful for capacity planning and stuff like that, but not for like low latency observability data, because sometimes these things just aren't predictable. So here we're talking about metrics forecasting. So given the metric, given the values of the metric, I want to predict into the future what's the expected value and put some sort of boundaries on it and forecast the metric. It can be useful for some subset of metrics, like how is your storage, what way is your storage growing, and what's your prediction at like an hourly level for the next 24 hours or something like that, for capacity planning or things like that. But typically at the low level, kind of second by second metrics and infrastructure metrics, it's not the most useful, because what's the point in some of these things? Number one, just aren't predictable. They're random noisy processes that, sure, they move around and they might have trends sometimes, but the trend is usually at a longer horizon than what you want to predict. And the longer out you forecast, your forecast just becomes basically rubbish, or just becomes like the average value. So people sometimes get a little bit carried away with this metric forecasting and stuff like that. It's still a valid use case, but you have to be kind of clear about thinking about in advance. Okay, what does I want to do with these predictions? What's the time frame I'm interested in, and how am I going to use these predictions? And obviously then the main thing here is to start as simple as possible. So literally start with the dumbest model you can use, which oftentimes is some sort of rolling average or moving average. There's a little bit slightly more fancy versions you can use, like exponentially weighted moving average. But if you can't prove value with a simple model here and actually making use of the outputs, then you definitely shouldn't spend time going crazy with these fancy deep learning, Facebook profit models and forecasting, because that's just going to be a whole lot of work and it's going to be painful. And if you're not even sure, what the use you're getting out of it, then you need to be very careful. So yeah, and obviously like you need to match your data to the horizon you're interested in predicting. So obviously you can't use second level data to predict hours in advance. You have to obviously aggregate first, and so you have to it has to be all at the same granularity. And so yes, forecasting is valid, but you don't just blindly try and forecast everything. Is the one little tip there. Kind of be a bit more thoughtful about how you use it. And so when I originally did this deck, I had like 10 use cases, and I only came up with 9. But in the meantime, we have now turbo chatbots. So that was the 10th use case, which is chatbots for everything basically, and that's kind of what we're seeing in the last few months. All right, we have chatbots for everything, even in observability. Everybody seems to now have a chatbot. I'm a little bit on the fence, but there is definitely use to things like chatbots and like natural language interface to observability systems. But there's a little. I think we're not there yet in terms of how well they understand like a whole complex system of metrics and logs and traces. There's like a whole. You would almost need to build like a whole layer of new APIs that are kind of language model friendly APIs that sort of summarize little insights into cards basically, and then these cards almost become like documents that you can then use things like retrieval augmented generation on in like real time on your infrastructure. That something like that could very well be useful, where you have like a RAG architecture on top of all your data, and it's also kind of adapting and evolving in real time, and so that definitely could be useful. But I haven't seen it fully done yet. But I wouldn't rule it out, and there's definitely use cases where things like alert understanding and general sort of Q&A type approaches with different chatbots for observability definitely for sure would be useful. So it's kind of still an open area. I think there's not really any obvious silver bullet here, but it's worth exploring. So that's pretty much it. That's all those 10. That's kind of my 10 use cases. I have some links here and stuff, but I'll put the deck in in the in the uh, in the video notes. And there's more kind of, I have like, we have some observability hot takes. We have some ML blogs of stuff we've been working on. We have some of these are also exist in this like little NetData ML app that I did. It's very rough proof of concepts. And some of the stuff we've implemented, it's available in our NetData demo room. Basically, you can just go play with it. Mainly that's the anomaly detection, change detection, and some alert ranking. Well, we have an anomaly detection based alerts as well. So yeah, that's it. Thanks for watching.